In this section, we're going to talk about resistors, which are very important and omnipresent components in electronics. We'll define what is resistance. We'll talk about resistor in series and in parallel. We'll discuss the Kirchhoff voltage and current laws, and in the end, we'll also talk about electric power. What is resistance? The resistance of a component is the ratio of the voltage applied and the current that flows through it. So if you take a device, you apply a certain voltage to it, you measure the current that goes through it as a result of it, and you make the ratio between the voltage and the current, what you get is the resistance. So if you want to write it in an equation, this is it, V divided by I is equal to R. That is usually how resistance is indicated. This is called Ohm's law, and the unit of measurement of resistance is Ohm. Let's look at a little example. Let's say we have a circuit like this one represented on the right. We have a battery, so it's a voltage generator. Let's say this battery is a 1.5 volt battery. And then what we connected here to the circuit is a piece of material. So it could be anything. You could connect wood, you could connect metal, or really anything you want. So as a result of the 1.5 volt applied to this material, we're going to have a certain current I going through the material. And again, as described before, if you do the ratio between the voltage 1.5 volt in this case and the current, you get the resistance of the material. The resistance of a material represents how much the material opposes to the passage of electrons. So in this case, we have a battery. So as we said before, the anode of the battery is full of electrons. These electrons really want to go to the cathode of the battery, which is the positive terminal. Now we have a closed loop, a closed circuit here, so it's possible for this electron to go and reach the cathode. So what's going to happen is that the electron is going to start to travel, go through this ideal wire here, reach this material. Now inside of this material, the path of the electron is probably not going to be straight, because the material itself is made of atoms. So as the electron is trying to go through the material, it's going to bounce around. It's going to hit an atom, change direction, do something like this. So bounce a little bit around, but eventually it's going to find its way out, and it's going to reach the cathode. Let's try to understand the difference between power and energy with another hydraulic example. So here we have a little system with a cistern. Cistern is a big tank full of water, and this big tank is at a certain elevation compared with the turbine, and let's call this different in height h, and let's say that is equal to 100 meters. Then we have a valve that can be open and closed, so allowing the water to flow down through the turbine, and the turbine is just a device that can be used to convert the energy of the water into electrical energy, for example, to power a house. Now let's do a little bit of a calculation to see, first of all, what is the energy that is stored into the system. As we've seen before, because we have a certain amount of water with a certain mass at a certain elevation, that is equivalent, that means that the water will have a certain potential energy, in this case, gravitational potential energy. So here we have a few numbers. Let's just do the math. So we have been told that the volume of the system is 10 cubic meters. So as a consequence, because this is water, we have a weight of 10 tons, so 10,000 kilograms. So now the energy, U, it's equal to mgh, where g is the gravitational acceleration, which is roughly equal to 10. So if you substitute, so the mass is again 10 ton, g is about equal to 10, and h is about 100. So in the end, what you get is about 10 megajoule. So this is the energy that is stored into the system that can be used to produce a certain amount of work. The way you produce the work, in this case, is by opening the valve, letting the water flow down, and turn the turbine so that the energy can be converted into electric energy. Now, let's say we have a certain flow of water that is equal to 1 cubic meter per second. So when you open the valve, you have 1 cubic meter per second of water coming down. So now, in this way, we can easily calculate what is the power that is transferred from the water to the turbine. So we have 1 cubic meter per second. Now this cubic meter, each of the cubic meter has a weight of 1 ton. And then we can multiply by the acceleration of gravity and the height. So in this case, you see, it's kind of a similar equation. We have the mass, we have the acceleration, and we have the altitude, and all of that divided by second, meaning this is an energy that we are transferring every second. So this is equivalent to, if you do the math, 1 megawatt. So this is the amount of energy that is transferred every second from the system through the turbine. So in this case, because we have 10 megajoule and we are delivering a power of 1 megawatt, that means that after 10 seconds, all the energy will be consumed. What is a resistor now? A resistor is an electronic component that is specifically designed to have a certain resistance. So a resistor usually in schematics have this symbol here. Sometimes when I draw by hand, it will most likely look more like this, just because it's kind of hard to make this shape. But it's a very simple component to use and to understand. As we said before, you put it in a circuit. If you know what is the voltage across the device, you can calculate the current very easily by dividing the voltage by the resistance. And vice versa, obviously. If I tell you what is the amount of current going through the resistor, you can immediately calculate the voltage across the device by multiplying the current by the resistance. Down here, there is an example of a resistor, just in case you ever open an electronic device. This type of resistor are called through-wall. They are not the latest and most modern components because they're quite big, but they're still used in the industry quite a bit. In order to push electrons through a resistor, you need to spend some energy. So this energy is initially in the form of potential energy, as if you remember, the voltage across the resistor is basically a representation of the potential energy that the electrons have. The potential energy is converted into kinetic energies, and that's how the electrons are pushed through the device. But then, as the electrons go through the resistor and hit the lattice of the material, they will convert the energy into thermal energy that will increase the temperature of your resistor. So if you take a circuit without a battery, and nothing is connected, there's no current, you measure the temperature of your resistor, and then you connect a battery to it, and all of a sudden you have a current going through the resistor, you wait some time, you measure the temperature of the resistor again, you will see that the temperature of the resistor is increased. The first time we talked about current, we made an analogy between current and a water stream. It's an analogy that works really well, as you can think at the current as a stream of electrons. Now we're going to extend that analogy to include also the voltage and the resistance. This analogy should help you understand better these concepts. Let's talk about the hydraulic circuit first, on the left on the slide. At the bottom we see there is a reservoir of water. You can think of this as a big lake or an ocean. Simply is a place that has so much water that no matter what you do with your little circuit, you're not going to be able to influence it at all. Close to the reservoir, there is a low pressure, and this is a characteristic of the reservoir as well. Again, because this is directly in contact with the reservoir, if the reservoir happens to have a low pressure, all the rest of the circuit in direct contact with the reservoir is going to have a very low pressure as well. There's no way you're going to change that. Then we see we have a pump. The pump is able to change the pressure from low to high. That's exactly the goal of the pump, to apply a certain pressure to the water so that the water will actually flow through your circuit. Then your circuit is simply made of a big tube with pretty big cross-section. So the water is really free to go around your circuit. But then you see that at some point here, you actually have a choke, a point where the cross-section of the tube becomes much smaller. So it's going to be much more difficult for the water to go through that. You can say that this choke is applying a resistance to the flow of the water. It's pretty easy to understand what is the electric equivalent of this hydraulic circuit. The flow of the water, it's clearly the current, equivalent of the current. The pressure is the equivalent of the voltage. So we have low pressure, low voltage, and high pressure, higher voltage. The pump is the equivalent of a battery, like a device that is able to change the pressure from one point to another. And the choke is the equivalent to the resistance. So we have the equivalent circuit here on the side. We have a battery, again, which is equivalent of the pump, high voltage at the top, low voltage at the bottom, a resistor in between. And we know that through the Ohm's law, we are able to calculate that the current that will flow through this circuit will be equivalent to the difference in voltage divided by the resistance. At the same time, the flow of the water through this hydraulic system is equal to the difference in pressure divided by the resistance. Not all electronic circuits can be explained using the water analogy. For now, this water analogy is very useful to understand in an intuitive way the relationship between voltage, battery, current, and resistance. The Kirchhoff voltage law, abbreviated with KVL, is one of the most important laws that you need to know in order to solve electronic circuits. As indicated on the side here, this is the definition of the Kirchhoff voltage law, and it basically says that the sum of all the voltage in a loop must be equal to zero. What is a loop? A loop is any path traced from one point in the circuit around other points in the circuit and then back to the initial point. So very simple definition. How do you actually implement that practically speaking? So I'm just going to show you very simply with an example on the right. So you see here a simple circuit. It's actually the most complicated circuit you have seen so far. We have three components. We have a battery, we have two resistors, R1, R2. Now we don't know exactly what is the value of the resistor, and that is not really important. We know that the voltage of the battery is equal to 5 volts, and we know that the voltage across one resistor is equal to 3 volts. Now, what is the voltage across the resistor R2? Probably very simple to understand what is the voltage at that point, but some circuits might be more complicated than others. And so it is important to understand what is sort of a formal procedure to follow to make sure your result is always correct. It's pretty simple to implement. So what you do, let me take my green pen, is that you identify the loop. Here we only have one loop, so there's no doubt. You pick a random direction for the voltages. That is already done. And when I see a random direction, I mean apply a random orientation for the arrow of the voltage. Like in this case, we know, okay, the 5 volt is in this direction, so the potential is higher here than here. We know that 3 volt is in this direction. V2, we don't know yet what is the direction of the voltage. It could actually be directed the other way around. It doesn't matter. I decide that the voltage most likely is directed in this direction, so there is a higher potential here than here. So that is totally random. Then you assign a direction of the loop. So you have this loop, you just write a circle here, and you decide, let's use this direction as a convention. Any direction is fine. You can be clockwise or counterclockwise. And now all you're going to do is that you're going to sum all these voltages together, and the one that goes with the same direction of the circle are going to be positive. The one that goes with the direction opposite of the circle, they're going to be negative, and the total sum has to be equal to 0. So in this case, 5, it's going in the same direction of the circle, so I'm just going to write plus 5. Now when I get here, 3 is the opposite of the circle, so minus 3 volts. V2, I don't know what is the value, but I can clearly see that it's going in the opposite direction of this arbitrary orientation, so minus V2. And now we completed the circle, so equals 0. Now this equation can be solved. I will give very easily the solution, which is V2 is equal to 2 volts. Easy, right? The example that we have looked at before, it's a very simple one because clearly there's just one loop in the whole circuit. If you consider a more complicated one, like this one on the right, there could be many more loops here. The Kirchhoff voltage law applies for any loop that you can possibly choose. That will always be true. So in this example, that is one loop. It's already highlighted, but let me take a different color, blue for example. This is another loop. This is also another loop. You can also choose a loop that works like this, or you can also choose a loop that does something like this. Any loop is a fair game. You can choose any loop you want. And if you apply the Kirchhoff voltage law the way that I just explained, you will always be able to solve the circuit. Another very important law of electronics is the Kirchhoff current law, which is abbreviated often with KCL. Here's the definition of the law. The algebraic sum of all currents entering and exiting a node must be equal to 0. A node is any point on a circuit where two or more circuit elements meet. In this example on the right, we have two nodes, A and B. And most of the time, people use a dot to represent a node. The procedure to calculate all the value of the currents is very simple. You first define an arbitrary direction for the currents that you don't know. In this example, we already been told what is the value of this current and the direction of the current. We already been told the direction and the value of this other current. We don't know the value of the current in this branch of the circuit. So as far as we can tell, the current could be going down or up. We don't know that yet. So what we have to do is to apply an arbitrary direction. It doesn't matter what you pick. If you pick the right direction, you will get a positive number as a result. If you get a negative number, you knew that the direction was the opposite. Now, to calculate the current I, the missing one, you just apply this simple rule. So you take a certain node. You could take A or B. In this example, they are exactly the same. Let's take A. So if we look at A, this current, this 1 amp current, is entering A. So we can write plus 1 amp. The 0.3 amp current is leaving the node, so we can write minus 0.3 amp. And the current I that we're trying to find is entering the node, so it's plus I, all equal to 0. It's very simple to solve this equation. I is equal to minus 0.7 amp. So the fact that the current is negative means that the real direction of the current is actually the opposite, which completely makes sense. If you think about it, you have 1 amp going into this node, and if 0.3 amp are going down, 0.7 amp have to be going in the other direction. The Kirchhoff current law is a representation of the principle of conservation of charge. It simply means that you cannot destroy or create charges out of nothing. So if I tell you that there are 3 charges going into the node in this direction, and I'm also telling you that there are 2 charges going in this other direction, you can be sure that you're going to have 1 charge going in this other direction. Otherwise, if that wasn't the case, that would mean that some charge somehow disappeared, or you create some charge out of nothing, which is impossible. I want to show you that it doesn't matter which node you choose. Ultimately, there is only one solution for the current in the circuit. So let's do the same calculation using node B instead of node A. So now the 1 amp current is obviously coming out of it. So it's minus 1 amp. The 0.3 current is coming inside of it, so 0.3 amp. And the current I that we're trying to find is leaving the node, so it's minus I is equal to 0. So as you can see, we get exactly the same results. I is equal to minus 0.7 amp. And that has to be the case. Otherwise, that means we have committed some mistake in the previous calculation or in this calculation. Real circuits are much more complicated than the one that we are dealing with for now. Usually they are made of many more components. So it's really important to learn a few tricks that allows you to simplify the circuits, or even just to understand what's going on even when there are a lot of components. The circuit on the left has 4 components. There is a voltage generator, and there are 3 resistors, R1, R2, and R3. These 3 resistors are in series with each other. The same current will go through the 3 resistors, because obviously just looking at the circuit, there's really no other way to go for the current. In the middle of the screen, we have another circuit where we replace the 3 resistors with an equivalent series resistor. So what we're trying to do here is we're trying to simplify the circuit, and we're trying to find what is the value of R series. That for the same voltage V, so the exact same battery is applied to the R series resistor, will give us the same current as the series of R1, R2, R3. So we really try to simplify the circuit. If the goal of the 3 resistor was to generate a certain current from the voltage of the battery, or if we replace the 3 resistor with an equivalent resistor, nothing is really changed. In order to calculate the equivalent series resistance, we'll have to use Ohm's law and the Kirchhoff voltage law. The way we're going to do this is very simple. We have V and we have I, and we have R1, R2, R3. So V is an input because it's the battery that we placed here. What we want to do is we want to, from these circuits, from the original circuit on the left, we want to calculate the values of I. Of course, we're not going to be able to calculate the value in terms of amperes, because we don't have the value of the voltage, we don't have the value of resistance, so we will never know the actual value of the current. Our goal is to calculate I as a function of V, R1, R2, R3. In order to do that, the first thing we want to do is to give a name to the voltage across the three resistors. So because the resistors are called R1, R2, R3, we're going to call the voltage V1, V2, V3. The orientation of the arrow of the voltage is random. Of course, I know already what is the result, so I put the smart way to put this the orientation, but even if you place it upside down, you can still get the right results if you follow the Kirchhoff voltage rule. So anyway, just random orientation from the top, and that's it. So now, using Ohm's law, I can write the value of V1 as a function of I and R1, because V1 has to be equal to R1 multiplied by I. And for the same reason, V2 is equal to R2 multiplied by I, and V3 equal to R3 multiplied by I. Very simple. So now, if we use the Kirchhoff voltage law, like this, I can decide a certain random orientation. It's very easy to write that V has to be equal to V1 plus V2 plus V3. So now you can see that here we have all the elements, right? We define V as a function of V1, V2, V3, and V1, V2, V3 has been defined as a function of R1 and R2, R3, and I. So now if we replace V1, V2, V3 with the definition of V1, V2, V3 from these three equations, we get the V is equal to R1 multiplied by I, R2 multiplied by I, plus R3 multiplied by I. Now we can collect I, because this is, we have the sum of three terms, and all three terms have I. So if we collect I, we obtain R1 plus R2 plus R3. If we do this, very easy to calculate what is the value of the current as a function of V, R1, R2, R3. So the current I will have to be equal to V divided by R1 plus R2 plus R3. Now, what we're trying to do with this exercise was to find a value for the resistor R series that will give us the same current for the same voltage applied V. It's very easy to see from this very equation that the value that R series has to be to give you the same current I is equal to R1 plus R2 plus R3. So R series will be equal to R1 plus R2 plus R3. To conclude on resistor in series, here we have like a generic statement that you can keep in mind. So let's say you have a certain number of resistors in series. So in this case, I'm assuming, from R1 all the way to Rn. So it doesn't matter what is n, and it could be 100, it could be 1000, it doesn't matter. You can sum as many as you want. The series of a certain number of resistors is equivalent to a single resistor whose value is equal to the sum of the value of all the other resistors. So in this case, all these resistors in series will be equivalent to just one resistor called R series, whose resistance is equal to R1 plus R2 plus R3 plus all the way till Rn. Let's now look at what happens with the resistors in parallel. The circuit on the left, there are two resistors, R1, R2. In this case, they are not in series, but they are in parallel. Components that are in parallel share the same voltage. That is fairly easy to see. Voltage is defined between nodes of a circuit. And here we really only have two nodes. One node is this one, node A, and the other node is this one, node B. You see that between these two nodes, you can only define one voltage between these two nodes. So automatically, the voltage V that is generated by the voltage generator or a battery is going across both R1 and R2. Now, depending on the value of R1 and R2, we can possibly have different currents I1 and I2, or they could also be the same if R1 and R2 are the same value of resistance. What we want to do here is exactly the same as what we did before for the resistor in series, which is we want to find the value of R parallel a value of a single resistor that has the same effect as the two resistors R1 and R2 in parallel. From a point of view of the voltage generator V, whether there are two resistors, one resistor, 1,000 resistors, a mix of series and parallel resistor, it doesn't matter. The net effect of having two resistors on one resistor will be to generate a current I from a voltage V that the voltage generator has created. So from the point of view of the generator V, having one or two resistors doesn't make a difference as long as the resulting current I is the same. So what we want to do is exactly that, to find what is the value of our R parallel, as I call it here, that actually has the same effect as the parallel of R1 and R2. In order to do that, we will make use of the Ohm's law and also the Kirchhoff's law. In particular, we'll adopt a similar strategy as done before. If you take R parallel and you write it in terms of Ohm's law, what you can write is the following. R parallel is equal to V divided by I. So V is kind of like an input because it is defined by a battery. We don't know what is the value, but it's a certain number. I is really the incognita here, right? Because the I, it really depends on the resistor, R1, R2, and so on. So what we're going to do, similar to what we've done before, is that to use the circuit to the left, the first circuit, calculate the value of I relative to V from using the Kirchhoff's law and Ohm's law. And then once we've done that, we'll replace the value of I into this equation. Because I will be dependent on V, V will simplify, and in the end, we'll just have a value of R parallel, which uniquely depends on R1 and R2.